All right, we're on to example number 6, where we're going to do the operation of multiplying complex numbers. Now, if you're not awake right now, if you're feeling sleepy, you need to wake yourself up because this one is quite a doozy. This one's going to be quite a bit to follow along with. I think this is the most important example because this is the one that actually applies to the real world the most. This is where complex numbers actually find their use in the real world. And this is one example of it. This is an example found in electrical engineering. And I will try to generalize what kind of situations would allow you to use complex numbers in a way that hopefully starts to kind of make sense. Okay, so let's just look at this example. They say the voltage V of an AC circuit, AC meaning alternating current, something where the electricity is being pumped backwards and forwards. There's a light bulb here, something, electricity is going back and forth, and that current causes the light bulb to turn on. Okay, so the voltage of an AC current can be found using the formula V equals CI, where C is current and I is impedance. If C equals 3 plus 2J amps and I equals 7 minus 5J ohms, determine the voltage. Okay, let me give you a little physics lesson real quick. So let's not talk about electricity. Let's just talk about a hose full of water, like a garden hose. Okay, so current in that sense would be how fast does the water travel through the hose? Is it going very slowly, trickling through, or is it shooting right through the hose? Okay, so that would be current. Voltage in an electrical circuit would be analogous to pressure. So pressure would be like, okay, if you have the hose and it kind of trickles out and falls out versus when you put your thumb over it at the end and it shoots out real hard, that is pressure in fluid dynamic terms. Voltage is very similar. So pressure in a hose is kind of measuring how hard are each individual water molecule being pushed along. Voltage is measuring how hard is each individual electron getting pushed along. So a high voltage means the electrons are getting pushed very hard. A low voltage would be the electrons are being pushed kind of gently along. Okay. Impedance is kind of a slightly more complicated version of what's called resistance in physics. It's described with the unit ohms. It is just how much does the material itself, does the wire the electricity is passing through, want to resist the motion of those electrons through it. So that would be kind of like if you imagine putting a bunch of rocks inside the hose that got in the way of the water. Or if you thought about like traffic on a highway, if there was a lot of traffic, that keeps the traffic from flowing. So anyways, impedance has to do with how much does that wire want to resist the electricity passing through it. All right, so those are kind of your physics ideas here for a moment. Now, looking at this equation, we are dealing with something where the voltage is related to two things. It's related to the current and the impedance, when you impede something, I guess is probably the better way to pronounce that. Okay, when we have two numbers touching here, so we're talking about multiplication. We're not talking about addition where we have two things that add up. We're talking about multiplication. So a good way to think about this is usually to think about what happens if I hold one the same and I change the other. Okay, so for example, if this equation says that the voltage is always equal to the product of these two, let's say we keep the current constant. So we're going to keep the current, the speed at which the electricity flows through the wire, that's going to stay the same. We're not going to change it at all. But I do want to change something else. I want to change how much resistance there is, how much it's impeded along the way. So I'm going to change what type of wire it is and make it so it's harder to get that current through. But I'm going to try to keep the current the same. So what am I going to have to do? Well, I'm going to have to push that current through harder because I have to push it through all that resistance. So for example, if I doubled the impedance, I would have to double the voltage, keeping the current constant. Okay, that's the relationship here. If I double I needed double V as long as C was kept the same. If I cut the resistance in half, if I cut that impedance in half, then I would only have to provide half as much of a push to get the current going at the same speed. Okay, what happens if we keep the impedance the same? So we don't change how much it resists the motion of the electricity. We are just going to change the current. Well, if I want to double the current and keep this one the same, I'm going to have to push twice as hard. If I want to cut the current in half, make the current go a little slower, then I'm going to push half as hard. Okay, this is what it means for the voltage to depend on the current and the impedance. Okay, so what we are doing here when we multiply complex numbers is we are providing a tool to describe situations where one thing depends on two other things. Okay, that's kind of the main point of what you would apply this towards. Any situation where one thing depends on two other things. Now, why does it need to be complex numbers? Why can't it just be regular numbers? I mean, you can imagine lots of situations where you can have an equation like this, where if you had real numbers in these two positions, it would follow that pattern I described just as well. Okay. Now, the reason why we use complex numbers is because complex numbers are a tool that allow us to describe how vectors interact with each other. Okay, a vector is if you've never taken a physics class, what a vector is, it's a number that has a direction also. So if you think about like wind speed, you don't just say how fast the wind is moving, you say how fast is it moving, and is it going north, is it going south, east or west? I don't know if my image is flipped from yours. I will assure you I know which direction east and west is, whether or not that looked right. We can think of other things that have directions. Your velocity, how fast you're going, you usually measure that in a certain direction. You don't just say, I'm going 60 miles per hour. You say, I'm going 60 miles per hour towards some certain place. Okay, so when you have these vector quantities, these numbers that have directions to them, you can draw them on a graph. So don't worry too much about all the numbers on here quite yet. But what this graph is showing is that in this example, we have a current that has a certain strength, but it's not just that it has a certain strength. It has a certain strength and it goes a certain direction. Okay, that's the way the current's going. Now the resistance also has a direction. In this problem, although I'm not totally certain that this is a realistic numbers for a real world situation, but just let's take the numbers as they are. In this problem, they're saying the resistance is kind of in this direction. It resists motion, not along the current, but kind of almost parallel to the current. Okay, so actually it's probably not getting in the way too much at all because most of the current is not really going in this direction. Okay, but there's a certain amount of resistance, certain amount of impedance. Sorry, I keep using resistance. It's the word I'm more familiar with, in that direction. And now we want to say, okay, we know that the voltage, the amount of pushing force, is a product of those two things. Well, it's a product of two vectors, and when you multiply complex numbers that are on the complex plane, where you're charting on the x-axis real numbers, sorry, I got a smudge there, but real numbers, and on the y-axis, we're plotting imaginary numbers. Now, this is not an I, this is a J, because in electronics, in circuits, they use J. It's just a thing happens in math and physics. People like to use different letters in different situations just to keep things straight, and it also kind of confuses people at the same time. So sorry about that. All right, so when you're plotting on the complex number plane, the number plane that has real numbers in one direction and imaginary numbers in the other, it allows us to do these operations where we multiply vectors. So we multiply one arrow by another arrow, and we get some answer, which is our final result, which is some new vector. Okay, in this case, the vector points out in this direction, goes out to 31 and minus J, which would be, way out here somewhere. I didn't draw the graph small enough to get it on there. But that's saying that the pushing force is pushing in this direction. Okay, so let's see how I got all these numbers anyways. On the question, it gave us 3 plus 2J amps and 7 minus 5J ohms, and it asked us to multiply those. Okay, so I'm just going to show you that on an area diagram. This is how I like to show multiplication. In my mind, visually, multiplication I always do in terms of rectangular areas. That makes the most sense to me visually. So 3 plus 2J times 7 minus 5J. Well, the 3 and the 7 make 21. 7 and 2J makes 14J. Negative 5J and 3 makes negative 15J. Negative 5J and 2J makes negative 10J squared. So all in all, we got 21. We got negative J. We had one more negative here than the positives. And we get minus 10J squared. Well, J squared, this is our imaginary number squared, so that's negative 1. So we get plus 10 rather than minus 10, which brings our 21 up to 31. That's how I got my answer of 31 minus j. And I will work that out not by that area model, but in the model that the book is showing, just so that I can kind of show you what the book wants to see. And that is going to be done like so. So they're going to use the FOIL method. Now, I'm sure lots of you are comfortable with the FOIL method, doing first, outer, inner, last. So the first would be 3 times 7. The outer would be 3 times negative 5j. The inner would be 2j times 7, which is that 14j. And the last would be 2j times negative 5j. Flip my screen over so I can write a little better, because that's getting pretty wiggly looking, isn't it? Okay. Now these are, once again, just all of the things that I just showed you in those boxes, right? We have our 3 times 7. We have our 3 times negative 5. Okay, so anyways, you just saw that. So we're getting what we had before. Now we're going to simplify it in the boxes. We're going to say we have 3 times 7 is 21. They've done this next one for us, the negative 15j that we got right here. We're going to say 2j times 14j is 28j squared. I think I'm messing that up somewhere. Okay, let me just double check. First, outer, inner, 2j times 7. Yes, that should be 7 there. I put the result ahead of time. So if you caught that, good job. Times 7 would be 14j. 21, our real number, can be combined with this negative 10j squared like we did before. What order are they doing that in? 21 minus 15j plus 14j. Yep, so they put the j's together. So minus j minus 10j squared, where we have j squared equaling negative 1. Okay, 21 plus 10 equals 31. Same thing I showed you with the area model. I always find the area models a lot more straightforward than the FOIL method, just because this is all just kind of abstract numbers where physical shapes and sizes make more sense to me. Now you might say, well, how does it make sense when like these are imaginary units, so they're not really real lengths? That'd be correct. So this is not to scale. This is not showing a physical object, but it still shows the mathematics of multiplication just as well if they were real numbers all the way through. All right, so if you needed to pause that, watch that slower, rewatch it, I would advise you do so. I will reiterate again, this is the example that has the most real world application. It is not only in electronics. There's a lot of stuff where in quantum mechanics, which you learn about in really high level chemistry and physics classes, maybe in college, you would hear about this. There's lots of applications, but the main thing, like I said before, was it's all about multiplying those vectors, multiplying those quantities that have a size and a direction. I will post a video at the bottom, which I was watching this summer, that goes into detail on this over the course of about an hour. Feel free to watch it if you find this an interesting topic. I would recommend it, although it is not required in any way. It's just up to your own intellectual curiosity to take you down that path. All right. Well, thank you for keeping up with that explanation. And we have one more left before we're done today.